My name is Dr. John Watson, and today I am privileged to chronicle a most unusual Sherlock Holmes case, the adventure of the missing factors. Holmes and I had just sat down to an afternoon snack of tea and crumpets, prepared by our esteemed landlady, Mrs. Hudson, when Holmes exclaimed, "Ah, Watson, we are about to have a visitor." And sure enough, we soon heard the downstairs bell ring, and Mrs. Hudson escorted to our door our newest client, Nicholas Witherby, who had a most unusual story. Yesterday his curio shop was robbed, not of anything of great value, but of two little inexpensive statues that represented numbers, from a collection of 10 such statues. He thought nothing of it at the time, until he was contacted by one of his competitors, who had a similar experience. Holmes was immediately intrigued, grabbed his coat and hat, and beckoned me. "Come, Watson, we must act at once. The game is afoot." And so it was that we went to Witherby's curio shop, where we found the 8 remaining numerical statues, each representing a different number. It didn't take Holmes but a few seconds to study the 8 remaining statues and place them on the counter in a uniquely Holmesian manner. He put the 1 on the left and the 48 on the right, with a generous amount of space in between. Then 2 on the left, 24 on the right, 4 on the left, 12 on the right, 6 on the left, 8 on the right. He studied the situation for only a few seconds and then exclaimed, "That's it, Watson. There is evil behind this theft, and I know exactly who is behind it. None other than Professor James Moriarty, the brilliant but misguided mathematician." More striking was his next comment. "Watson, I know exactly which 2 statues were stolen. Do you?" When I confessed my complete ignorance, Holmes chided me. "Watson, you must know, it's obvious." I never ceased to be astounded by Holmes, but I confessed my shock. "How could you possibly know?" To which Holmes replied, "Watson, you know my methods. Certainly you saw how I placed the statues. They're all factors of 48, and I placed them in pairs, outside in, the 1 and 48, the 2 and 24, the 4 and the 12, and the 6 and the 8. Do you still not see the clue?" Once again I confessed my ignorance, to which Holmes responded, "Watson, look at the 6. "What does that tell you?" But I had no idea. Holmes continued, "Just think of the divisibility test for 6. A number is divisible by 6, if and only if it's divisible by 2 and by 3. We have the 6, and we have the 2. But where is the 3? It is missing. So 3 must be one of the 2 missing statues." "Now I see the 3, but how do you find the other missing statue?" I asked, and Holmes replied matter-of-factly, "Just take 48 and divide by 3 and see what you get." So you can see the other missing statue must be 16. I had to confess my admiration for my friend's thinking, which now appeared only so obvious. "Where did you learn this, Holmes? At the university?" "No," said Holmes. "At Brompton Academy?" "No," said Holmes. "Where then, my good friend?" To which Holmes replied, "Elementary, my dear Watson, in elementary school. And Watson, be sure to record the 3 and 16 in that little notebook of yours." We then went to the curio shop owned by Witherby's friendly competitor, David Moore, and found a similar situation. There were a dozen statues originally, but 2 were stolen that same evening. As before, Holmes carefully placed the 10 remaining statues on the counter. He placed 1 on the left, 60 on the right, 2 on the left, 30 on the right. And before he could go on, I interrupted him. "Why do you keep placing the statues outside in? That is very annoying and confusing." "Ah, Watson, I'm so glad that you ask. I actually have 3 reasons. First, it allows us to capture the factors 2 at a time. With the 1, we get 60. With the 2, we get 30, and so on. So we cut our work virtually in half. Second, by going outside in, our list will always appear in order, least to greatest. We will have no rearranging to do at the end. And third and most important, we eliminate other factors along the way with absolutely no work. Look, do you see the 1 and the 2? There are no whole numbers between 1 and 2, in fact, just fractions and decimals. So there can be no factor between the 1 and the 2. Therefore, there's no factor between the 30 and the 60. So without any work, we've eliminated 31, 32, 33, and so on, all the way up through 59. Why, that's almost half of the whole numbers between 1 and 60. Good grief, Holmes, that saves us an enormous amount of time. Time? Time? Did you say time, Watson? I'm going to remind you of the irony of that remark in a little bit. And Holmes resumed his placement of the statues. He placed 3 on the left, 20 on the right, 5 on the left, 12 on the right, 6 on the left, 10 on the right. Watson, what's missing this time? But again, I didn't know. The 6 was there, but so were both the 2 and the 3. I did remember that because the 60 ends in a 0, 10 is a factor, and because 10 is a factor, 2 and 5 are also factors, but all of those statues were there too. I give up, Holmes, I said. Look at your pocket watch, Watson. What time is it? Why, it's 3:15. But what does that have to do with anything? Watson, you see, but you do not observe. Time is based on the number 60. So the various parts of the watch give us the factors of 60. There are 60 minutes in 1 hour, 30 minutes in a half hour. There are 12 hours in the clock, each 5 ticks or minutes apart. You see, all of the factors of 60 are right on your watch. Now, what time did you say it was? 3:15. Well, Watson, that's 3:15. And you said it's 3:15. And that's because there are 4 15-minute intervals in an hour. The missing factors are 4 and 15. 4 times 15 is 60. So our missing factors, our missing statues are 4 and 15. Again, I begrudgingly had to admire Holmes' thinking as I jotted down those numbers 4 and 15 in my notebook. At this point, Holmes concluded that we really had to visit all of the curio shops in London, and so we went to them, one at a time, discovering in each case that they too were robbed, with nothing of great value missing beyond 2 numerical statues in each shop. In the third shop, again we found that numerical statues were missing, but the proprietor did not know which ones were stolen. As before, Holmes lined them up carefully on the shelf. He placed 1 on the left, 63 on the right, 3 on the left, 21 on the right, and then he stopped because there were no more statues. Only 4 statues had remained. Sherlock beckoned me to identify the identity of the 2 missing statues, but with less information, I was completely baffled. Come now, Watson, there are at least 4 ways to figure this out. Just give me one. But I was unable to produce any method, and quite doubtful of Sherlock's boast of 4 ways. Holmes, you are a genius, of course, but there's no way you could have 4 different ways to figure this out. Ah, Watson, do you really doubt me? First is just a simple multiplication fact. 7 times 9 is 63. Second is the test for 9. Take the original number 63, add up the digits. 6 plus 3 is 9. Now 9 is divisible by 9, and therefore 9 is a factor of the original number 63, and 63 divided by 9 is 7. Again, we find that 7 and 9 are the missing factors. Third, consider the combination of factors 3 and 21. 3 times 21 is 63. Now, Watson, give me two numbers that multiply to 21. 3 and 7. Very good, Watson. So let's split up 21 into 3 times 7. Now, join the 3 times 3 together to get 9, and we have 9 times 7 is 63. Again, we find the same two missing factors. This is called using the associative property of multiplication. Holmes, very nice, but you did promise 4 different methods, and I now challenge you to come up with a 4th and different way to identify the missing factors. Do you still doubt me, Watson? But I'm glad, because now I have a chance to show you my 4th and favorite method. And I say favorite because it only works in very special circumstances. Notice the original number 63 is 1 less than 64, which is a perfect square, the square of 8. That means the square root of 64 is 8. And when this happens, the number before that perfect square, 63, is the product of the two next door neighbor numbers to that square root. Therefore, 8 having neighbors 7 and 9 gives us 63 is 7 times 9. That's remarkable, Holmes, I had to admit, as I dutifully recorded our two missing factors, the 7 and the 9. I wish I knew that when I was memorizing my multiplication facts. But tell me, Holmes, why do you need 4 different ways to find the same answer? Isn't one way good enough? Of course, Watson, only one way is needed, but your way may be different than my way, and that might be different than our proprietor's way. We might not see one strategy, but we might see another. Or a method that works in one problem may not work in another. It's a lot like a golfer having different clubs for different situations, and like you having a number of different instruments in your medical bag. In mathematics, we call this number sense. On to our 4th curio shop, where there were 12 numerical statues initially, but only 10 left. This time, Holmes permitted me to place the remaining statues. I carefully put 1 on the left, 84 on the right, 2 on the left, 42 on the right. Noticing that 84 has the sum of the digits being 12, which is divisible by 3, I put 3 on the left, divided into 84 to get 28 on the right. It was easy to see that 4 was a factor, and 84 divided by 4 is 21. Noticing that 2 and 3 were factors, I saw that 6 was a factor, and dividing into 84, I got 14. Well, Holmes, I said, it looks like there's none missing. It looks like we have all the factors. In fact, I was pretty proud of myself and hoping to impress Holmes. Watson, are you sure? I commend these 4 statues to your attention. The 14, the 21, the 28, and the 42. Watson, what number do you think of when you see those 4 numbers, 14, 21, 28, and 42? Why, 7, Holmes. They're all multiples of 7. Precisely, my dear Watson. So 7 is one of the factors. Dividing by 84 by 7, I found that 12 is the other missing factor. Holmes, I wonder, is there an easier way to get that 12? Well, Watson, let's take a look. We know that 6 times 14 is 84. And we know that 14 is 2 times 7. Again, we can associate the 2 with the 6 to make 12. And 12 times 7 gives us 84. Again, I was impressed with Holmes' work as I recorded the 7 and 12 in my notebook. The fifth curio shop also featured 10 remaining statues, which Holmes again asked me to display. I placed 1 on the left, 90 on the right, 2 on the left, 45 on the right, 3 on the left, 30 on the right. I see the 2 and the 3, Holmes, as I placed 6 on the left, 15 on the right, and then 9 on the left, 10 on the right. Holmes, I have it. 10 is a factor, so 2 and 5 are factors. We have the 2, we're missing the 5. 5 is one of the missing factors. Excellent, Watson, but what is the other factor? Well, I said, let me use your method. 9 times 10 is 90, and we can pull our 5 from the 10, giving us 2 to combine with the 9 to make 18. 18 is our other missing statue. Brilliant, my dear Watson. There is hope for you yet. Our sixth visit was to the west end of London, where the curio shop once again had 10 remaining statues. Holmes again took charge of arranging the statues. He placed 1 on the left, 126 on the right, 2 on the left, 63 on the right, 3 on the left, 42 on the right, 6 on the left, 21 on the right, 7 on the left, 18 on the right. What's missing, Watson? Why, nothing, Holmes. Everything is there. Watson, don't be deceived. Our list may look crowded, but there's something missing. Add up the digits of 126. What do you get? 9. Of course, Holmes. So 9 is a factor. But what's the other factor? Do we have to divide? Is there another way to do this? Well, try this method. Let's take 126 and let's remove a very nice number of 9s, since 9 is a factor. Let's remove 10 9s. That would be 90. What's left? An easy subtraction, 36. How many 9s are in 36? 4. So we're removing 4 more 9s to get down to 0. So how many 9s did we remove altogether? 10 plus 4? 14 9s. 9 times 14 is 126. Write down that 9 and that 14 in your little notebook. Our next visit was to a small curio shop, also on the west side of London. Here again we found that 2 of the 6 number statues were missing. I placed 1 on the left, 98 on the right, 2 on the left, 49 on the right, but that's all the statues there were. Watson, what's missing? I don't know, Holmes. Watson, what do you think of when you see the number 49? Well, I think of 7 times 7 is 49. 49 is a perfect square. Excellent, Watson. So let's take that 49 and break it into 7 times 7. The matching factor to 49 was 2. So let's take the 2 with the 7 to get 14. Or if you like, take 98, subtract 10 sevens, leaving 28, which is 4 more sevens. And again we see that the other factor is 14. So our missing factors are 7 and 14. Our 8th visit was to the south side of London, where we found the proprietor very perplexed. He had many expensive new shipments in his inventory, but the only items missing were 2 of his 6 numerical statues. I quickly laid out the 4 remaining statues. I placed 1 on the left, 171 on the right, 3 on the left, 57 on the right. I then added up the digits 171 to make 9. The test for 9 works, so I know that 9 is a factor. And I like that last method of Holmes, so I took 171, subtracted 10 nines, which is 90, leaving 81, which is 9 more nines. So I knew that I had 10 plus 9, or 19 nines. So the missing statues, 9 and 19. Bravo, said Holmes. Now let's go to our final curio shop. I'm getting very hungry. With that, Holmes and I traveled to our final shop, which, coincidentally, happened to be close to the Grenadier, one of our favorite eateries. The proprietor of this shop was quite disorganized and did not keep very good records of his inventory. Nonetheless, he did show us his remaining number statues, not knowing how many he had at the outset. We found 7 statues in our midst. Looking them over, Holmes seemed rather excited. Ah, Watson, I hope you remember our trip to the States when we visited New York. I didn't understand what he meant, but proceeded to lay out the statues. I put 1 on the left, 100 on the right, 2 on the left, 50 on the right. And then I realized what Holmes was referring to. Holmes, I get it. This is American currency. There are 100 pennies in the American dollar, 2 50-cent pieces in the American dollar. There are 4 quarters in the American dollar. And there are 10 dimes in the American dollar. But we only have 1 10. One of the 10s is missing. Watson, you are right. 10 times 10 is 100, but we don't repeat factors, so there only needs to be 1 statue of 10. But you are missing 2 other statues. What other American currency are you familiar with? Why, the nickel. There are 20 nickels in the American dollar. So we're missing the 5 and the 20. Yes, Watson, you're right on the money, and just in time because it's time for supper. Be sure you have your notes with you, because when we get back to Baker Street, we have work to do. As was his custom, Holmes did not discuss the case during the entire meal. Back at 221B Baker Street, Holmes took out a large sheet of paper and asked me to list for him the 18 missing numbers representing the 18 stolen statues, 2 from each of the 9 curio shops. I read off these 18 numbers as Holmes wrote them down. 3, 16, 4, 15, 7, 9, 7, 12, 5, 18, 9, 14, 7, 14, 9, 19, 5, and 20. "That's it, Watson," Holmes said, barely containing his excitement. "What do you observe, Watson?" "Why, there are 18 numbers, and they include some repeats." "Holmes, what does it mean?" "I call to your attention, Watson, that the largest number is 20, despite the fact that over 1/3 of the remaining statues displayed numbers higher than that." "What does that suggest to you, Watson?" "Absolutely nothing, Holmes. A mere coincidence. Far from that, my dear Watson. Think of our English alphabet with only 26 letters, so we don't need any number beyond 26. It's obvious. The 18 stolen numbers represent a number letter code. I have written several monographs on the subject, and more often than not, the code will not be very complicated. Moriarty may be brilliant, but his accomplices are not. So, Watson, let's try a very simple letter-number substitution code and see what we get. Above each number, let us place the corresponding letter of the English alphabet and see our sequence of letters. The third letter of the English alphabet is C. The 16th letter is P. And so on. We continued placing the letters above each of the numbers. Clearly, Watson, this doesn't spell out anything recognizable. The message must be scrambled. Let's look for words that we can find within the letter arrangement. What do you see, Watson? I see dog and ring and set. Excellent, Watson. Knowing Moriarty, let's try the word ring and see what's left. Okay, Watson, can you find a word that might fit with ring? I see dog and God and set and gold. That's it, Watson. If we take the letters gold, then we have gold ring. So let's remove the G, the O, the L, and the D and see what's left. Holmes took out another sheet of paper and wrote down the remaining letters. C, P, I, G, E, N, I, S, E, T. So far, Watson, we have gold ring. But what do you see are our remaining letters? I see pig and set and sing and sign. That's it, Watson. Not sign, S-I-G-N, but signet, S-I-G-N-E-T. Once again, Holmes took out a clean sheet of paper. He wrote down the message we had so far. Gold, signet, ring. And he wrote down the letters that remained. C, P, I, and E. Watson, what do you make of this? Why, Holmes, if we had the letter R, we'd have the word price. If we had another E, we'd have the word piece, P-I-E-C-E. Brilliant, Watson, except we don't have another R or E. We have no other letters, but we do have the word epic. That's it, Watson. You have solved the case. The code translation is epic gold signet ring, and that must refer to the large Greek gold ring called the Theseus ring, now on loan at the Victoria and Albert Museum from the National Archaeological Museum in Athens. We read about it just last week in the Daily Telegraph at breakfast. It was purchased for over 66,000 sterling pounds, but is considered invaluable, and its theft would precipitate an international crisis. Moriarty must be planning to steal it and use the statues to convey this information to his agents. We must notify Scotland Yard's at once. Come, Watson, let's pay a visit to Inspector Lestrade. Armed with this information, the burglary of the epic Theseus gold ring was thwarted that very evening in progress. 5 men were arrested at the Victoria and Albert Museum, but the nefarious and clever Moriarty could never be tied to the crime. He, of course, was not one of the 5. After Lestrade informed us of the safety of the Theseus ring, Holmes and I spent the rest of the evening in our comfortable quarters, I tending to some medical reports before retiring for the night, while Holmes could be heard playing Mendelssohn on his Stradivarius violin into the wee hours of the morning. And thus ends the adventure of the missing factors. Future videos will be going into specific topics relating to finding factors of a number. This will include divisibility test, prime factorization, and using prime factorization to find factors, to predict how many factors a number has, and even to predict the sum of all the factors of a number. These videos will assist you in finding the factors of a number and checking that you have found them accurately. And they will feature the tessellators and Merlin the Wizard. Stay tuned.